Jupiter is a giant ball of gas, bigger than all the other planets in the solar system put together. Jupiter spins like a top. It has the shortest day of any planet, turning once on its axis in less than 10 hours. Glimmering feebly through Jupiter's ring of dust, the Sun is but a beacon 780 million kilometers distant. So remote that it takes Jupiter nearly 12 years to orbit the Sun. Jupiter dwarfs our planet. It takes 11 Earths to span Jupiter's diameter, and over 1,300 to fill its volume. Where comets are concerned, Jupiter is like a vacuum cleaner. This comet, on a journey from the fringes of the solar system, swings a little too close. It's captured by Jupiter's gravity. Subject to forces hundreds of times greater than the pull of the Moon on the ocean tides of Earth, the comet fragments. It's July 1994, and more than 20 pieces of comet Shoemaker-Levy 9 plunge towards Jupiter. (1977). From our little blue planet, twin space probes head for the outer solar system. They're the Voyager missions, whose first target is Jupiter. 2 years later, the planet fills their sights. It's like no other. There's no surface, no solid features, just gas whirling in gigantic belts of weather. The belts blow in opposite directions, eddies and storms racing round the planet. The biggest is the Great Red Spot, a tempest 3 times the size of Earth, an anti-cyclone that's raged for centuries. At the top of the screen, the red spot seen from Voyager 1. Below, from Voyager 2. 10 years later, from Earth orbit, the space shuttle launches Galileo. By way of Venus and twice past Earth, it's 6 long years to Jupiter. Galileo makes it. In 1995, a probe is deployed for a descent into hell. The plunge is slowed by parachute. Every second is vital for research. The clouds thicken. Winds blow at 500 kilometers an hour, driven by Jupiter's heat. Temperatures soar. Jupiter generates far more heat than it receives from the Sun. The core is 30,000 degrees Celsius. 40 minutes in, and the atmosphere is 10 times denser than Earth's. 1 hour in, and the Galileo probe expires, crushed by the pressure. Jupiter is 90% hydrogen, the rest mainly helium. Haze tops the atmosphere. Then crystals of ammonia, ammonium hydrosulfide, water ice, and droplets of water and ammonia. Deeper to hydrogen and helium, liquid hydrogen, metallic hydrogen, and a rocky core. It's this liquid metallic hydrogen that generates Jupiter's magnetic field. This donut-shaped zone buzzes with electrified particles. But Jupiter's magnetosphere stretches much further. After the Sun, it's the biggest entity in the solar system. And where the solar wind funnels toward the planet, auroral halos display around the poles as charged particles interact with the upper atmosphere. The 16 moons of Jupiter. Having launched its probe into Jupiter's atmosphere, Galileo now turns its attention to these satellites. First to Io, a moon flexed by the tug of Jupiter and the pull of a neighboring moon. The result is erupting volcanoes, first pictured by Voyager. Io is the most volcanically active body in the solar system. It heaves with eruptions. Lava relays the surface over and over again. Plumes feed the sulfurous atmosphere. By contrast, this moon is placid, Ganymede. At minus 150 degrees, the icy crust is 100 kilometers thick. Ganymede is the largest moon in the solar system, bigger even than the planet Mercury. Around Ganymede, Galileo detects a weak magnetic field. It hints at the internal structure. Beneath the crust, a mantle of slush, then a layer of rock and ice surrounding a silicate core. Another of the moons, Callisto, could be Ganymede's double, except for the craters. They record eons of bombardment. The greatest impact site, a vast ringed basin. And here's another, imaged by Galileo. If there's extraterrestrial life in the solar system, it could be here, on Europa. Smooth and cracked like an eggshell, there's a theory that the whole moon is an ice-covered ocean, a possible medium for life. For the waters may be warm, heated by the gravitational flexing caused by Ganymede and Io. But this ice could be many kilometers thick. To penetrate the ocean and search for organisms must await a landing. Nevertheless, the grooves and fissures crossing the surface are cause for hope. They're reminiscent of frozen oceans on Earth, and what life teems beneath their ice. The Big Four of Jupiter's 16 moons, a mini solar system. Liftoff for Cassini, last of the big spenders. It's 1997 and 5.5 tons of spacecraft head for Saturn. Cassini reaches this distant giant in 2004. The mission costs $1 billion. So what prompts this costly and lengthy undertaking? Our world is just 150 million kilometers from the Sun. Cassini must go past Mars, the last of the terrestrial planets, and cross the Great Divide to Jupiter. Saturn is beyond. This beautiful planet is nearly 10 times further from the Sun than is Earth. Its solar orbit takes almost 30 years. Its daily rotation, 10¼ hours. After Jupiter, Saturn is the largest planet. So buoyant that in an ocean big enough, Saturn would float. Yet it could swallow Earth nearly 750 times. Like Jupiter, Saturn is gas, 94% hydrogen, the rest mainly helium. And it has similar weather bands, but haze makes them hard to see. They're revealed by changing the camera filter. They're full of storms and eddies. Winds are faster than on Jupiter. This jet stream, for example, blows at more than 1,500 kilometers an hour. Saturn's atmosphere has 5 layers, with haze at the top, then crystals of ammonia ice, ammonium hydrosulfide, water ice, and water droplets. Deeper still to hydrogen and helium, then liquid hydrogen, metallic hydrogen, and a rocky core. As with Jupiter, it's the metallic hydrogen that generates Saturn's magnetic field. It diverts the solar wind, except where electrified particles funnel toward the poles. They generate aurorae. Watch the North Pole. From afar, the rings of Saturn are like gossamer. Seen close, they are billions of moonlets, from specks of dust to icy rocks the size of trucks. On a scale we can appreciate nearer home, the rings stretch so wide that they'd fit between our planet and the orbit of the Moon. But they are no more than a kilometer thick. From the Earth, our view of the rings changes as Saturn orbits the Sun. It's because of the tilt of the axis, 26 degrees. Edge on, the rings virtually disappear. Our knowledge of the rings is through the Voyager flybys of the early 80s. They reveal 7 main bands, each with hundreds of ringlets. And they record time-lapse of mystery spokes, possibly dust, levitated above the rings by electrostatic forces. With a background star as reference, Voyager catalogues the rings and their divisions. The largest gap is the Cassini division, 4,000 kilometers wide. Some of the rings are kept neatly in orbit by little shepherd moons. Here is a pair marshalling the outermost ring. This moon, called Pan, orbits within the Encke division itself. But the rings are a puzzle. They may be the debris of pulverized space rocks, too close to the planet to clump together as moons. Within a few million years, the rings of Saturn may well disperse. Voyager time-lapse of Saturn and its moons. There are 18 known satellites. Tiny Mimas is one of the oddest. Ice and rocks and a gigantic crater. Had the projectile that caused it been bigger, Mimas might have become another of Saturn's rings. Enceladus, nearly twice the size of Mimas, but still just 500 kilometers across. Plains of ice, formed perhaps of water, welled up from beneath. Icy fountains may still spurt here as Enceladus is flexed by the pull of its neighbors. Next in Voyager's sights, Tethys, over 1,000 kilometers across with a great canyon just visible at the underside. Dione is similar but with one hemisphere brighter than the other, an icy surface of craters and troughs. A close-up of Rhea, a big moon, 1,500 kilometers wide. Iapetus has one hemisphere coal black, the other snow white. Tiny Hyperion is like a distressed hamburger. And this little rock periodically swaps orbits with a twin. Saturn's biggest moon, larger than the planet Mercury, is discovered by telescope in 1655 by the Dutch astronomer Huygens. The moon is Titan, and it's a little like early Earth in deep freeze. Titan is veiled in haze, but Voyager senses the presence of organic molecules, carbon-based compounds like those that sparked life on Earth. We can only guess at the surface, for Voyager sees nothing through the all-enveloping smog. Look forward to Cassini. On its arrival in 2004, Cassini deploys a lander, appropriately named Huygens. The descent takes 2.5 hours. The atmosphere is rich in nitrogen, just like Earth. Data is flashed to the mothercraft and onward to Earth. On landing, Huygens has just 30 minutes of life. The temperature is minus 190 Celsius. There's no sun for solar panels, and it's snowing ethane and methane. Titan may have oceans of hydrocarbons, but Huygens can also handle a splashdown. Again, only half an hour to signal Earth with those vital clues. Is Titan a laboratory for life? That's reason enough for this billion-dollar mission to the Lord of the Rings. Seventh planet from the Sun and orbiting on a strangely tilted axis, Uranus inhabits the twilight zone of the solar system. Uranus is a gas giant with rings and moons. This one, Miranda, is the rough diamond of the solar system, a rocky little ice chip with cliffs taller than Mount Everest. It's cold out here. Uranus is 19 times further from the Sun than is planet Earth. (1977). A star winks as it passes behind the planet. The winks reveal the rings of Uranus. Astronomers count 9. Subsequently, 11 are confirmed. They emphasize the severe tilt of the planet, all of 98 degrees. Uranus orbits on its side. With a diameter of over 51,000 kilometers, it's far larger than Earth. But compared to Jupiter, that's modest. Uranus may be a giant, but Jupiter is a supergiant. (1986), and from Voyager, the first close-up. An apparently featureless ball. With infrared, the Hubble Space Telescope sees a little deeper. It spies 3 hazy layers of atmosphere. There may be weather down there, but it's obscured. The moving arrow shows the odd angle of the magnetic field through Uranus. Compared to the rotational axis, the magnetic axis is offset by 60 degrees. On Earth, the shift is only 11 degrees. The atmosphere is mainly hydrogen, with helium and a touch of methane. The upper band is a narrow layer of haze rich in hydrocarbons. Below, hydrogen and methane, then ammonia and hydrogen sulfide, and a transition zone of gas and liquid. Deeper still, liquid hydrogen, a mantle of ice, and a rocky core. Uranus has 17 known moons. One of them, Miranda, is shattered early in its life. Some of the debris forms the rings of Uranus. The rest reassembles into Miranda Mark II. That's the theory. It's unproven, but it does explain the rings. Or perhaps Uranus was struck by a body the size of Earth. That could account for both the icy rings and the tilted axis. Either way, the chaotic contours of Miranda are like a moon reconstructed. Miranda, less than 500 kilometers across, is a riot of geological form. The most spectacular, these ice cliffs up to 15 kilometers high. Fall from the top in this puny gravity and it would be 14.5 minutes before you hit the ground. This moon, by comparison, is dull. It is aerial, more than twice the size of Miranda, a network of canyons, faults, and frost. Umbriel, a little bigger, has an ancient surface, pockmarked with craters. Titania has a canyon to rival Africa's Rift Valley. It's the largest moon, 1,600 kilometers across. Finally, Oberon, outermost of the big moons. Uranus, where a day is almost 18 hours and an orbit of the Sun takes 84 years. We've reached Neptune, the last of the gas giants and the last of the major planets. So remote that when it's surveyed by Voyager in 1989, radio data takes 4 hours to reach Earth. Neptune's solar orbit takes 165 years. This planet is 4.5 million kilometers from the Sun. Problems in predicting the position of Uranus led to the discovery of Neptune in 1846. Most of the time, Uranus is either ahead of or behind its calculated position. Something is disturbing its orbit. That something is Neptune. As Uranus on the inner orbit catches up with Neptune, so Uranus gains speed. But as it overtakes Neptune, Uranus slows down. By taking these disturbances into account, astronomers find Neptune. Neptune on the left is denser but slightly smaller than Uranus. Our planet would stretch across Neptune more than 4 times, a width of just under 50,000 kilometers. To span Jupiter, it would take 12 Earths or 3 Neptunes. After the blur of Uranus, Voyager sees plenty of weather on Neptune. Here, a cloud whips through the upper atmosphere. Neptune is the windiest of the planets. At the equator, gales roar at 2,000 kilometers an hour. The clouds are cold, minus 200 degrees. But the weather is driven by internal heat, something missing on Uranus. Voyager tracks a tempest the size of Earth, the Great Dark Spot. Over a number of days, it changes shape. Although the spot hurtles round the planet, this Voyager time-lapse holds its center of frame. To the southeast, another storm, the Wizard's Eye, bigger than any typhoon on Earth. Seven years later, through the Hubble Space Telescope, the Great Dark Spot is gone. Neptune spins once in 16 hours. The atmosphere is 85% hydrogen, 12% helium, the rest mainly methane. There are 4 distinct layers. The outermost is stratospheric haze with lots of hydrocarbons. Lower down, hydrogen and methane. Then ammonia and hydrogen sulfide, and a transition zone of gas and liquid. Towards the center, liquid hydrogen, a mantle of ice, and a rocky core. Neptune has 2 main rings. Parts of the outer ring thickened where material has clumped. In imaginary close-up, particles of icy dust. There are 8 confirmed moons, 6 discovered by Voyager, all tiny except one. It is Triton. 2,700 kilometers across, Triton has the coldest known surface, minus 238 degrees. Yet it spurts blackened nitrogen. These geysers shoot 8 kilometers high, their plumes carried downwind in the wispy atmosphere. Triton may be a captured asteroid. Like Pluto, the planet beyond, a world at the very edge. The Lowell Observatory, Flagstaff, Arizona. In 1930, the outermost planet Pluto is discovered through this telescope. Astronomer Clyde Tombaugh makes the find. He's 24 at the time. Tombaugh does it by systematically photographing the sky on large glass plates. He snaps each piece of sky twice, several nights apart. For several nights, he photographs twice in succession each region of the sky. Then, with this blinker, he compares the 2 images. If they're identical and nothing jumps, he's not interested. for only objects within the solar system move against the background stars. After 6 months of blinking, the dot that jumps is Pluto. Pluto and its moon Charon have a combined mass of less than 1/5 of our moon. Little frontier worlds of methane and water frozen in the outer gloom. On average, compared to Earth, they are 40 times further from the Sun. Far beyond is the Oort cloud, a swarm of freezing debris that shrouds the solar system like a sphere. Closer in is more icy trash, the Kuiper belt. Pluto, with its wide eccentric orbit, may well be a member of this belt and not a true planet. Like the comets that visit us from Kuiper and Oort, Pluto is a mixture of ices. This is comet Hyakutake in 1996. Its nucleus is a snowball 3 kilometers wide, but the tail stretches for millions of kilometers. As a comet nears the Sun, it grows 2 tails. The yellow one is fine dust, the blue gas. The gas tail detaches occasionally in the gusting solar wind. It's that wind, plus the pressure of solar radiation, that blows the tails away from the Sun. With the solar disk masked, here's time-lapse of a comet rounding the Sun. Here, comets plunging into the Sun. Comets are the vagabonds of the solar system. Some travel on random elliptical orbits, hurtling among the planets. Kamikaze comets die in the Sun. Others just graze it. Jupiter plays havoc with comets. This one is captured from its orbit around the Sun by the pull of the giant planet. The comet, a fragile mixture of ice and grit, is drawn within 50,000 kilometers. It pays the price. Jupiter tears it into more than 20 fragments, and it's just the beginning. The comet, named Shoemaker-Levy 9, is to stage the celestial show of the century. It's to plunge into Jupiter, carpet bombing the soupy atmosphere. The date, July 1994. The fragments create shock waves as big as Earth. The moment of an impact. Lower on the left, a plume shoots over 1,000 kilometers high. The most famous comet is Halley. It visits our skies once every 76 years. When the Italian painter Giotto saw it in 1301, he made it his Star of Bethlehem. The Bayeux Tapestry depicts the conquest of England by the Normans in 1066. The comet is overhead. On Halley's last visit, the first of the space age, we visit the comet. A craft aptly named Giotto is launched by the Europeans. It's the most ambitious of an international armada. For Giotto is to fly right through the inner coma, the cloud that surrounds the nucleus. It's 1986, and there is the nucleus, shaped like a peanut, 16 kilometers by 9. Vaporized by the heat of the sun, gas and dust vent from cracks in the surface. glare obscures the view. But Halley's crust is carbon black. The coma, fed by the jets of gas, is well over 1 million kilometers across, bigger even than the Sun. These icy rocks are part of the Kuiper Belt, a disk of debris just beyond the planets. This is where Halley's comet comes from, dislodged perhaps by a twitch in the gravitational interplay between the Sun and its neighboring stars. Halley is lucky. As solar gravity draws it inward, the comet swings round the Sun instead of tumbling directly into it. But Halley is now captive, trapped in an orbit that takes it out beyond Neptune, then back to the Sun, again and again. Halley has an orbit of 76 years. Longer period comets arrive from further out, comets like Hale-Bopp, the most spectacular of the late 20th century. 1997 is the year of Hale-Bopp. Here, in close-up, the spinning nucleus, 40 kilometers wide, swirling gas and dust. They stream from the hemisphere heated by the Sun, switching on and off as the nucleus rotate. At its closest to the Sun, Hale-Bopp sheds 1,000 tons of dust every second. But in the chill of the outer solar system, comets revert to type. They become tailless and inert. Historically, comets always have tails, and they're linked to death and destruction. But fear of comets isn't all nonsense. To this day, they are cause for concern. Had Hale-Bopp struck Earth, we'd all be dead. But that's another story. The space probe Stardust on a close encounter with comet Wild 2. Like sticky flypaper, this instrument is to collect samples as Stardust travels through the coma of the comet. But unlike Giotto, which relayed only data from Halley, Stardust is to send its samples home. Insulated in a capsule, resistant to a fiery re-entry through Earth's atmosphere, a precious package from beyond the planets. Retrieved from a soft landing in the polar wastes, these samples of Wild 2 will be unique, the first chance for scientists to examine particles unchanged since the formation of the solar system. The Oort cloud stretches 1/3 of the way to the nearest star beyond the solar system, and the comets are its messengers. Between Mars and Jupiter, a belt of asteroids have their orbits, rocky remnants from the birth of the solar system. They live quiet lives, but accidents happen. Collision, or a jolt from Jupiter's gravity, and an asteroid is knocked from its orbit. Drawn inward by solar gravity and with a nudge from Mars, this space mountain is now a projectile. It's 65 million years ago. 10 kilometers of rock and metal are on a collision course with Earth. Doomsday for the dinosaurs. Earth suffers a cosmic winter and mass extinction. A much bigger impact, 4.5 billion years earlier, gives us the Moon. Earth is struck by an asteroid the size of Mars. Debris splashed into space either returns to Earth or clumps together to form the Moon. It's good news, for the Moon slows our planet's spin and accelerates the evolution of life. By contrast, the Moon is lifeless and barren. No oceans, nothing hides its scars. Peer through a telescope and scars there are. 30,000 craters pockmark the surface. Each depression testament to an impact, uneroded by wind or water, a pristine record of wax from space. Per square kilometre, Earth takes as many hits. Strip away our atmosphere, our seas, our vegetation, and all geological movement, and this would be our planet. Impactors reach planets even today. Jupiter, 1994. The culprit is this string of pearls. Discovered 2 years earlier, they're fragments of the same comet, Shoemaker-Levy 9. Straying too close, Jupiter's Herculean gravity rips the comet into more than 20 pieces, like dust sucked into a vacuum cleaner. The fragments now hurtle for the giant planet at 60 kilometers a second. Were it not for Jupiter's pulling power, far more comets would get through to Earth. Imagine these bruises on our tiny planet. The plume of an impact, outshining the aurora. The shockwave of an impact. It is as big as Earth. Picture the consequences had those crags hit us. 1972, and this space rock almost does. 80 meters wide and moving at 10 kilometers a second, it could destroy a city. Luckily, it skips off the upper atmosphere and back into space. 1992, high school football on America's East Coast. A fireball stops play. The missile breaks up, and some chunks are recovered as meteorites, the name for any cosmic debris that makes it to the ground. Siberia, 1908. This projectile, 60 meters wide, doesn't reach the ground. It explodes in the atmosphere like a nuclear bomb. Over 2,000 square kilometers of uninhabited forest is flattened. Had this happened over a major city, millions would be dead. The asteroid belt is like an orbital motorway. Those that stick to the road are fine. Those that veer off threaten us. At least 100,000 asteroids cross the orbit of Earth. 2,000 are big enough to cause us problems. Robots are sent to assess them. This one is to rendezvous with the asteroid Eros. In its current orbit, Eros is harmless, but in 100,000 years, it may well be on target for Earth. We must make its acquaintance. Eros is 40 kilometers across, 4 times the size of the missile that slew the dinosaurs. If we're still around and we don't stop it, nobody, no life on Earth, will survive this rock. In 1999, a probe investigates another threatening asteroid. Currently in a Mars-crossing orbit, a gravitational twitch could send it our way. The probe is to report. This craft, Rosetta, is scheduled for a closer encounter. Launching in 2003, it's to fly by 2 asteroids and waltz with the comet Virtanen. A lander is to analyze the nucleus. Earth's space buzzes with eccentric comets and Earth-crossing asteroids. For every one plotted here, 20 or more are yet to be discovered, some posing the threat of global extinction. But we, unlike the dinosaurs, can react. We can build a parabolic mirror and tow it into space. There, it concentrates reflected sunlight on an Earth-threatening missile and scorches it off course. Another concept: giant pods that close with an enemy asteroid and attach to its surface. They release super sails that catch the solar wind and tug the intruder away. Or how about this device? Like a celestial outboard motor, it shunts the object to a safer course. But suppose there's too little warning. A space rock will hit us in weeks. Do we go for the nuclear option? Crude, simple, a last resort, a direct strike. And who can predict whether it would save the world? Given the political will, an international search program could hunt down most of the comets and asteroids that threaten Earth. With advance warning, defenses could be mobilized. But there is still the nightmare scenario. At the edge of the solar system, in the icy depths of the Oort cloud, the gravitational hiccup of a nearby star perturbs a comet. It begins a million-year journey toward the sun. 90% of our skies go unchecked for intruders. The comet takes us by surprise. "10 kilometers wide, velocity 20 kilometers a second. It's as big as the dinosaur killer." Armageddon. Extinction. A 100 million megaton explosion vaporizes New York City. The crater is 200 kilometers wide. A shockwave blasts outward, flattening everything in its path. It will travel around the globe. As a cosmic winter descends, the reign of humankind is over. The Pillars of Creation, one of the most spectacular pictures ever taken of the cosmos. It's part of the Eagle Nebula, where stars are born. A dying star in the Cat's Eye Nebula. Another in the Hourglass Nebula. Masterpieces from the Hubble Space Telescope. Seeing deep into space is to do with gathering light. The human eye does it by collecting light through a lens. This it brings to a focus on the retina at the back. But for a cosmic view, only a telescope gathers sufficient light. This telescope collects light with a mirror, bounces it to a smaller one, then to a third, and finally to a focal point at the side. But the clouds and dust of Earth's atmosphere impair the sight of even the most powerful telescope. The Keck telescope in Hawaii is halfway through the atmosphere at an altitude of over 4,000 meters. But atmospheric turbulence causes images to shimmer. It's like looking through water. In the Canary Islands, the Herschel telescope is perched way above the clouds. So too the VLT, high in the Chilean Andes. The initials stand for Very Large Telescope. 4 separate mirrors, each 8.2 meters wide, and each mounted on anti-distortion supports. They compensate for any flexing of the huge mirrors as they're turned toward different points of the sky. Pin-sharp pictures from the VLT. But for the very best observing, there's nowhere like the clarity of space. 1990, the launch of the Hubble Space Telescope from the shuttle. Deployed by the shuttle's robot arm, astronauts gently place the telescope in Earth orbit. A $2 billion eye in the sky, 600 kilometers above the planet. Free of the atmosphere, Hubble is to have the sharpest view of the universe. It's to see 10 times finer detail than telescopes on Earth, and to be 30 times more sensitive to light. That light is focused by 2 mirrors, then analyzed by 5 special instruments to the rear. But there's a problem. The center of the big mirror is too shallow. It means that light is arriving at 2 focal points instead of 1. Hubble's images are fuzzy, although computer correction helps sharpen them. From this to this. But despite the problems, there are triumphs. At the pivot of 2 galactic jets, Hubble identifies a massive black hole. The Andromeda Galaxy, and evidence that it once consumed another galaxy. Hubble discovers a double core. In the Whirlpool Galaxy, it spies a suspected black hole. And here, the remnant of a supernova. But Hubble needs repairs. December 1993, a shuttle crew suits up for the job. Hubble is grappled into the cargo bay. The first task is to replace the telescope's power supply, the solar arrays. They've caused a wobble. One array is furled for return to Earth. The other, which won't retract, is simply floated away. Hubble is designed to be serviced in space, but this is a major reconstruction. The new arrays look like rolled-up window blinds. They're secured to the telescope and unfurled. And now for the big moment. Riding the robot arm, this cosmic repairman opens the doors of the main instrument bay. Hubble is the size of a school bus. The instruments as big as telephone booths. Out here, you can't forget your tools. A complete kit is mounted at the end of the arm. The object is to install optics to correct the distortion of the main mirror. The least useful of Hubble's instruments, a light measuring device, is removed. It makes space for the corrective module. Next, the replacement of the camera that does 50% of Hubble's science. The astronauts work half the time by spotlight, for the telescope orbits Earth every 95 minutes, moving rapidly from light to dark. The new camera has its own built-in corrective optics, plus improved detectors. Thanks to the astronauts, the mission is a resounding success. An error 1/50th the width of a human hair is corrected. Hubble has 20/20 vision. For the Space Shuttle program, this is its finest hour. With new spectacles, Hubble fulfills its potential. The corrective optics work like a dream. Tiny mirrors, no bigger than a thumbnail, compensate for the distortion of the primary mirror. They bring incoming light to a perfect focus. Mars in exquisite detail. Even remote Neptune has features. But Hubble is best with deep space. Here, L-shaped images piece together the Orion Nebula, a vista of star birth. These are clusters of hot young stars. And this, the debris of a supernova. Hubble's view of the Lagoon Nebula. Never has a galaxy been observed in such precise detail. The Egg Nebula, in ordinary light and infrared. A galaxy seen through two different instruments, gas jetting from the core. Watch the power of Hubble as it penetrates a single spot in the sky, a region uncluttered by the stars of our galaxy or galaxies close by. Deeper and deeper. Finally, we're looking at some of the most distant galaxies ever seen, 4 billion times fainter than the limits of human vision. Hubble is unveiling our universe as never before.